Okay, let's finish section 3.4 by looking at another tangent line problem and then talk about the existence of the derivative. All right, let's go ahead and find the equation of the tangent line to this graph at x equals 5. So let's work out the derivative itself, and then we're going to use that to help us in the process. Okay, so yeah, let's just dive right in and go f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so this is a square root situation, so we are expecting to have to rationalize the numerator. Okay, so some of these end up being really recognizable after a while. So let's work this out. The limit as h goes to 0. Now plugging in f of x plus h. So let's be a little careful here. The whole radical, x is the input, and the input needs to be x plus h. And then there's that minus 1. Okay, minus f of x itself, so that's the whole radical again, x minus 1 over h. Okay, and actually looks like there's no cleaning up that we can do yet besides just go ahead and go straight for rationalizing the numerator by multiplying by the conjugate. So it's going to be a big conjugate here, x plus h minus 1. So all that stays the same. We just have to switch this to plus. Okay, everything stays the same except we just switch the sign in the middle, and only the sign in the middle, to plus. Okay, so let's continue. So if we FOIL this out, we do get the predictable cancellations, but I'll kind of walk through it again. So the first times the first, the radical will cancel, and we get x plus h minus 1. Okay, so that's from the first part, okay, that part. Okay, now for the outer parts, and again, these two are going to look really nasty, but they're going to cancel. So I'll go ahead and write it out. So the outer part is going to be plus, and there is x minus 1 in the radical times the other radical of x plus h minus 1. Okay, so that's the outer ones there. And then for the inner ones, we just get that same nasty thing, but it's all minus. So minus root x minus 1 and root x plus h minus 1. So those are nasty looking, but they cancel. Okay, and then in the back, the last times the last looks like minus, and the radicals will cancel, so we'll be left with just x minus 1. But be careful, there's two pieces in there. There's an x and a minus 1. And so since there's two pieces in there, I want to use extra parentheses to emphasize that that minus is going to have to distribute. Okay, common mistake right there. Okay, all of this is over the denominator. Okay, like I said, don't distribute this out, leave the h out. And so all of that is going to go x plus h minus 1 and plus root x minus 1. And don't distribute that h. Okay, so we should see some nice canceling. Like I said, that this big middle nasty stuff is perfectly opposite. And then let's distribute that negative in there. And we should be getting a significant amount of canceling now. So let's see, I'll write this stuff out. We've got x plus h minus 1 in the front, and then all of the middle stuff canceled, and now it's minus x distributing over here and plus 1. Okay, all of this stuff down there still. Okay, and then like I said, there should be some pretty nice canceling. So plus x and minus x, minus 1 and plus 1. All that's left on top is an h. And then that's going to do our nice predictable canceling. And careful, this is a minus 1. Yeah, that's a minus, okay? All right, so then we've got x plus h minus 1, like I just corrected myself, plus root x minus 1. Okay, and then here is that satisfying moment where we get to cancel that h, and now we can write this as the limit as h goes to 0 of 1 over x plus h minus 1 plus radical of the x minus 1. Now, don't write limit anymore because we're going to go with direct substitution. So 1 over plugging in 0 for h. So x plus 0 minus 1 plus x minus 1. And so with that h being a 0 there, it's just going to be root x minus 1 plus another root x minus 1. And those are exactly like terms. So we can write it as 1 over 2 of those root x minus 1. And no more divide by 0 problem with that h. There's definitely domain restrictions with a radical in the denominator like that, but that is the derivative. Okay, so let's write this f prime of x equals 1 over 2 root x minus 1. Now we're not done because we just found the derivative. They wanted us to find the equation of the tangent line at x equals 5. Okay, so the beautiful thing about the derivative is it gives us the slope of the tangent line anywhere we want. Okay, so we know that the slope of the tangent at x equals 5 is f prime of 5. So we did all that work and now we just plug this in. 1 over 2 root 5 minus 1. So that's 1 over 2 root 4, which is 1 over 2 times 2. So that is the slope of the tangent. Whoops, my finger slipped right there, I guess. Excuse me. Okay, so this 1/4 is the slope of the tangent line. Okay, at x equals 5, we also need to find out f of 5. So f of 5, because we need a point and a slope. So for f of 5, it's just the original function. So we get 2. Okay, so we have a point of 5, 2. Okay, so we have a point. And we have a slope. Once you have a point and a slope, go ahead and use y minus y1 equals m times x minus x1. So y minus y1, so the 2 from the point, equals m, which is that 1/4 we found, x minus x1, which is the 5. Let's distribute that. So we have y minus 2 equals 1/4 x minus 5/4, and add 2. We have y equals, and we will be done, 1/4 x. So minus 5/4 plus 2 over 1 is plus 8 over 4. Go ahead and do the scratch work so that I can avoid needing a calculator there. So then we get plus 3/4. Okay, so there you go. There's the slope of the tangent line, the whole equation of the tangent line. And actually, if you go back to the Desmos thing, I have that function defined, but if you want to change that to whatever you want, go for it. What was it? Square root x minus 1. So yeah, you could absolutely play around with Desmos there. And we wanted the tangent line at x equals 5. So you can go ahead and play around with that. And so I wanted the tangent line at x equals 5. So let's make a equal 5. And right there. And so let's see. The slope f prime of a is 0.25. Did we get 1/4? Yes, we did. Okay, and then 3/4 for the y-intercept, 0.75, looking good. Okay, so yeah, I mean, Desmos You already know I love Desmos. Okay, so here we go. Let's finish off this section with the existence of the derivative. So just kind of a discussion for the existence of the derivative. So you've been noticing that there are some, since the derivative itself is a function, there are moments where the derivative would be undefined. Okay, and remember that the derivative is the slope of a tangent line. And so let's talk about this in a couple of different ways that the derivative could be undefined. So the definition of the derivative included the phrase provided this limit exists, okay, every time. And I had to include that because it's important. This means that there are cases where a derivative does not exist. So here are just 3 quick examples that could show when the derivative might not exist. These 3 examples right here, these following graphs show functions whose derivatives exist everywhere except at x equals 0. Okay, and so let's talk about them. Okay, here's a line over here. It's bothering me of when my pen slipped down the page. Okay, so for this 1 over x function, obviously the derivative does not exist at 0 because the function does not exist at 0. So what's the slope right here? Well, it doesn't even make sense to talk about the slope of a function when the function doesn't exist at all. So for f of x equals 1 over x, it's undefined at 0, and so obviously the derivative can't exist there either. Okay, for this one, this is a little bit harder to think about for g of x equals absolute value of x. So the slope makes perfect sense everywhere on the left side. It makes perfect sense everywhere on the right side. In fact, this is just like a straight line. So the slope is constant on the left and it's constant on the right. But this moment right here at 0, that's a problem because the slope switches instantly. And so if you tried to work out, remember that the definition of the derivative is the whole limit process. And so g of x right here for absolute value of x, there is this sharp corner, okay? And I put that in quotes because it's kind of an informal observation there. But that means that if we calculated the derivative, that's going to lead to a limit that does not exist. Okay, so the limit from the left ends up being a different value than the limit from the right. And I believe we worked out the limit of the absolute value function approaching 0, and we saw that it did not exist. So anytime that you have a situation where there's a sharp corner, the definition of the derivative with that limit process is going to give you a limit that does not exist because it's different from both sides. Okay, so whenever you've got a sharp corner, you're going to have that the derivative does not exist at that moment. Okay, and then this last example here is another weird one where I've got the graph of the cube root function. Okay, so this is x to the 1/3 power. You could talk about the slope of this graph pretty much anywhere. It just makes sense. You know, it's always changing and changing. But right there, notice how it gets really weird and it goes really vertical. Okay, so if you could imagine what would be a vertical line right through there. Well, what's the slope of a vertical line? Do you remember that? Okay, a vertical tangent line at x equals 0. Remember that the slope of a vertical line is undefined. And so since the derivative gives us the slope of the tangent line, then obviously if the tangent line is a vertical line, the slope is undefined. It means that the derivative is undefined. And going back to Desmos, I think it will break if I try to change the function. And so again, I invite you to go ahead and change that function. Let's see, it was x to the 1/3. Okay, so here's the function. And right now I've got it set with a as 5, but if I set it as a is, so there's the tangent line, and notice that you can get a tangent line that tells you the slope anywhere you want, but look at how it starts getting perfectly straight up and down. And maybe if I adjust this a little bit, if I wanted a to be in between like -1 and 1, I can change this step to go by hundredths or something like that. I can make it go a little slower. But yeah, notice how the tangent line gives us the slope of this function anywhere we want. But if I let it go right down to 0, then the tangent line becomes a vertical line right there at the moment. And so Desmos is even telling me everything's crazy undefined. Even the derivative itself is undefined because we've got that vertical tangent line right there. Okay, so anytime that you've got a situation where there's a vertical tangent line, that's going to give you undefined right at that moment. Okay, so good visual aid. Okay, so that's kind of just talking it through. And then I've got this summary right here, and we'll pretty much wrap it up right here. Just the existence of the derivative. The derivative exists when a function f satisfies all of the following conditions at a point. Okay, so at any given point, the derivative exists if f is continuous at that point. If f is smooth, okay, so none of those sharp corners where the limit's different on each side, and f does not have a vertical tangent line. Okay, the derivative does not exist when any of the following conditions are true for a function at a point. So if f is discontinuous, then obviously there's no slope there, so the derivative doesn't exist there. Sharp corner automatically fails having a derivative at that point, or vertical tangent line automatically fails. Okay, so yeah, derivative exists only if all three of these are satisfied. And if any one of these three happen, then the derivative does not exist there. Okay, so very, very important topic right there in section 3.4, the derivative. Pretty much calculus is oftentimes divided up into two separate topics: differential calculus, which is all about derivatives, and then there's integral calculus, which is like anti-derivatives. And we'll get into that topic a little bit later in the semester. Okay, so hopefully you're kind of excited about calculus and derivatives and stuff moving forward. That finishes off section 3.4. Hope you have a good day.